We are discussing memory testing. In particular, we are looking at read-write memories or SRAMs. DRAM testing is not too different. In a DRAM, the main difference is the DRAM cell is very simple. Okay. It stores the value as a charge on a capacitance. Okay. So I can show you, can see, right? So this is a very simple cell. There is only one transistor. So when you select the word line, you are sending a 1 on this NMOS transistor, causing it to get selected. And at the same time, if the bit line is high, then you will have a charge, this capacitance will get charged, right? And that is like writing a 1, right? And similarly, if the bit line is 0, right, then if there is a charge on this, it will get discharged. So that way it will store as 0. Lack of charge is a 0, whereas having some charge is like a 1. So it's very simple. Unlike SRAM cells, which required 6 transistors, they require only 1 transistor. So as a result, the density of DRAM can be very high. So DRAM is therefore cheaper than SRAM, because you can afford to possibly have 6 times its storage capacity for this same area, right? So instead of 6 transistors, we have a single transistor. But DRAM can be slower, okay, because writing, as you can see, is dependent on charging. So it takes, you have to wait for this capacitance to get charged, or you have to wait for the capacitance to discharge. The other problem can be, see, after, let us say you write a cell, okay, let us say I have written a 1 to this cell and charges have been stored, then let us say I deselect this line. Okay, this word has been removed, I mean we have put a 0 on this, but unfortunately this transistor will not be a perfect open, it will still have some resistance. So over a period of time, this charge can get leaked. So it will start losing this charge over a period of time, and if you don't write anything into this cell for a very long time, okay, I write a 1, then for a long time, let us say I don't write anything to that cell, it is quite possible that the 1 will get leaked away and it will become a 0. So 1 may become a 0 if there is a prolonged time for which I have not done any update. So there is a need to refresh the DRAM cells. Okay, periodically you should refresh the content of the DRAM cells. So another fault that can occur in a DRAM is the leaking away of the charges, or a 1 becoming a 0 because of what is called as a sleeping sickness. Okay. It is like you lose the data because you did not do any activity. It's like you are sleeping all the time, right? And in the process of sleeping, this charge leaked away. Sleeping means lack of activity. So DRAMs must be refreshed, and in spite of refreshing, if you are losing, then you have that sleeping sickness problem. Okay, so we have looked at all kinds of fault models like cell stuck at faults, cell transition faults. So here we use this notation. The cell I is stuck at 0, cell I is stuck at 1. Cell transition fault means once the cell makes a transition to 1, it may not be able to come back to 0 or the other way around. Then there could be a coupling idempotent fault. That means I is maybe changing from 0 to 1, causing J to become 0. I is changing from J to 0 to 1, but this goes to 1, or this. So I is changing from 1 to 0, J therefore becomes 1 because of some coupling. There could be coupling inversion faults. So here the value will depend on the previous state. It will toggle. If I is changing from 0 to 1, J will toggle. And similarly, if I is changing from 1 to 0, J may toggle. And maybe address decoder faults. So the problem could be I have a memory and there is an address decoder fault. So when I try to write to location 5, which was here, maybe I am writing to some other location, or maybe I am writing to both of them. Okay, I was supposed to write to 5, but I ended up writing to both 5 and 10. It can in fact write to multiple locations because there could be many address decoder faults. It could be that it doesn't write to any one of them. Similarly, read from 5. It may read from a wrong location, or it may try to read from 2 different locations at the same time, and as a result some garbage will be read. Then there could be bridge faults. So I was trying to write a 0 and a 1 in 2 different locations, right? There is an AND bridge between them, so as a result both of them get 0. Or there could be an OR bridge because of which both of them will get a 1. Now these are all what we call as functional faults. Now how do I test for any of these faults? See, suppose I tell you that when I try to write to 1, make sure that there is no address decoder fault. Then the only way I can do it is I have to fill the memory with zeros and then write to that location 5. Okay, sorry, write 1 to location 5. Then read everything back to see if anybody else got changed. If I am reading other, I am supposed to get the value 1 only from 5, but if I get it from other cells also, that means there is some coupling fault, something is there, or it could be an address decoder fault. It may be difficult to identify what the fault is. Okay, we cannot diagnose. So write all zeros, then write 1 to location 5, read back, expecting 0. So this is the kind of test vectors that we are talking about. But see, we can't write 1 for each fault, right? We have to see how we can write the fewest number of tests which will uncover a number of faults. Okay. So there is no hard and fast functional test algorithm. There are many functional test algorithms. So one of them is like write some see, let us take this. So we can fill the thing with all zeros. This is called as a solid zeros test. So write all zeros and read back all the zeros. Okay, write all zeros. Write 0 to all locations. Then read back. And if you find a 1 in the process of reading, record that there is a problem. Suppose this one read, when I read, I got a 1. Obviously, there is some reason for that. It could be a cell stuck at 1, or it could be some coupling between, there could be an inversion coupling or an idempotent coupling between any one of the cells. It doesn't matter what the reason is, there is some problem. How long does it take to do this? If there are n bits in the memory, then we have to write n writes and n reads. Then we can go and write all ones pattern. See, we could also write a solid 1 pattern. So write 1 to all locations, then read back. If you find I am reading a 0 somewhere, then it could be because of a stuck at 0 fault or a coupling fault. So people have come up with other patterns. Okay, they have come up with things like, these are called as row bars. So write ones in these rows and write zeros in the other. And when you read back, you have to get the same pattern. If you get anything else, it could be because of some applying address decoder, etc. Then you can interchange. You can make these zeros and these ones. These are called row bars. A little more fancy pattern. We can write column bars also. You can imagine that I can write column bars. So I can then flip and write zeros here and ones here. Zeros here, ones here. So we write this pattern and read back, and if you don't find the pattern that you wrote, then declare that something is wrong. We can write a checkerboard pattern. These are called column bars. These are called checkerboard patterns. 1 0 1 0 0 1 0 1 1 0 1 0 0 1 0 1 1 0 1 0. You can imagine that this is an even better pattern. Only thing is, the hardware to produce this pattern may be more complicated. Column bars, maybe it's not so difficult to write. So you will need a small hardware module which uses counters, etc. to generate these patterns. Right? Then there is, you can invert this. So you can write 0 1 0 1 1 0 1 0 0 1 0 1 1 0 1 0. These are called checkerboards. You can write what is called as a parity pattern. See, address of this is 0 0 0 0. The address of this is 0 0 0 1. The address of this is 0 0 1 0. The address is 0 0 1 1. Okay. Now I can take the parity. Let us say I am looking at even parity. Then that means the total number of zeros in the in these bits should be even. So it's already even, so I'll put a 0. Here the number is 1, so to make it even I'll put a 1. Here there is only 1 1, so I'll make it 1 in order to achieve even parity. Here I'll put a 0 because I already have two ones. This is 0 1 0 1. So two ones, even parity, so put 0. This is I'm sorry, this is 0 1 0 0, isn't it? So this should be 1. This should be 1 because this is row 1 column 0. Row 1 column 1, we already have 2 bits, so 0. 0 1 0 1, 0 1 1 1, and so on. Let us say this is 1 0 and this is 0 0. So 1 0 0, then 1. So this could be another pattern. So this is known as parity pattern. So the number of ones in the address find the number of ones in the address, then if it is even, write 0, else write 1. So this could also be a pattern. So like this, why is this, maybe this is a better pattern for address decoder faults. Each one of these patterns has certain advantages and certain disadvantages. See, this one may be fairly easy to produce, right? I need a counter to keep counting the row addresses, I need a counter to keep counting the column addresses, and I need a circuit to generate the parity. So it's not very difficult. They also come up with other patterns like galloping patterns. What does this do? I'll write all zeros. I'll start with this. Then the next step, I'll write a 1. So here write all zeros, then write 1 in address 0000, then read back all cells. So only one of them must be a 1, that is 0000, everything else should be 0. If there is a coupling fault because of which something else has become a 1, then that is a fault. Then I can go here, I can write back 0 and move this to 1. So this 1 moved, and again write 1 in address 0001, then write 0 in 0000, read back all cells, and so on. Finally it will do this. And after that it will read back all the cells. So you can imagine this will take a lot of time. If there are n bits or n cells, then we are writing a 1 in each of those cells and then reading back everything. So it will take at least n square read write operations. This n square can be very big because the number of bits in modern SRAMs is very large. So today n is of the order of 10 to the power 9. Okay. So this will become 10 to the power 18, which is a very large number. So you can calculate how big that number is multiplied by the time it takes to do a read and write operation. So you will realize that it will take a lot of time. So this is known as a galloping pattern. It's called galloping ones. And you can apply galloping zeros also. You can fill the ones in the beginning. then start galloping a 0. So write a 0 in 0 0 0 0. Read all back, read all cells. So here write all ones and so on. The last pattern will be 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. So this is a galloping 0. Same problem. It is also going to take order n square. Okay. So these are very hard to pattern. So difficult to practice. When n is large. For small memories, it's okay. If you have a 1K memory somewhere, don't worry about it. You can do this. Even the control algorithm may be slightly complicated. Okay, you have to write this galloping pattern test, right? The hardware to generate the addresses, etc., may not be trivial. So, since galloping patterns are hard to do, people have also found out marching tests. What is a marching test? So here also initially you may want to write all zeros. So these addresses are 0, 1, 2, 3. Let me label the addresses. So this address is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So these are the addresses in the increasing order. So there is a notation. We say in the increasing order of addresses, write 0. So that is what we just did. If we say in the decreasing order of addresses write 0, then we'll start from 15 and go backwards. If the order is not important, we do like this. That means it doesn't matter which order, 0 to 15 or 15 down to 0. So essentially what we are doing is for row equal to 0 to 3, for column equal to 0 to 3, memory of row column equal to 0. So that is what is happening. But we don't want to keep writing such complex for loops, etc. So this is a shortcut notation. So this was given by Professor Van de Goor. Okay, Van de Goor was a professor in Netherlands, I think in Delft University. And he developed this notation so that it's easy to talk about them. So initially we may write all zeros, and then what we are going to do is we are going to start marching a 1. That means we write a 1 and the others are 0. And then we are going to, unlike in galloping pattern, we are not going to read everything back. Okay. We are going to go and write a 1 here. Then we are starting to fill with ones. So it will go like this, and in the end we will end up writing all ones. So this is called marching a one. Unlike a galloping, where it sort of we replace this one with a zero. Only at any point of time, only one of them is a one or a zero. But here, over a period of time, everything, all the zeros will ultimately become all ones. So if you write something like this, for all rising order, write 0, then read back 0, then maybe write back 1, then write back. So this is the notation for marching tests. And what does it mean? Start from location 0 and go all the way up to 15 and keep writing zeros. Then start from 0 to 15 and simply read. Okay. So this marching has already happened. You have marched a 0 and filled everything with 0. Then read back just to see whether something has changed. We expected a 0, but if you get a 1 here, there is a problem. Then start from the address 15 and go down to 0 and write once. And then read everything back, and this time you have to read a 1 back. We are expecting a 1. So R0 means read and compare with 0. R1 means read and compare with. If we don't get, then there is a problem. So we remember, okay. So what really will happen is something like this. For I equal to 0 to n minus 1, okay, cell I equal to 0. Then for I equal to 0 to n minus 1, if read cell, if cell of I is not equal to 0, then remember this location. So initially location is, let us say, an empty list or empty set. Add I to location. This cell is bad. And same for I equal to 0, n minus 1 down to 0, cell of I equal to 1. Then if for I equal to n minus 1 down to 0, if cell of I is not equal to 1, then add I to location. So by the end of this, log contains the faulty cells. Okay. So those cells have some problem with them. This is corresponding to this. In the increasing order, write 0. In the increasing order, read 0. In the decreasing order, write 1. In the decreasing order, read 1. So that is the code. We don't write all this fancy stuff. Okay, we don't have to write for loops, etc. Instead of we just write a very top level algorithm like this. Okay, these are called marching tests. And there is no one way to do the marching. Okay, you can think of so many different marching tests.